So that's what we're going to do tomorrow. And you might be asked to do one not using components. Okay, so just like in chemistry, when you're trying to create a balance, you're trying to have an equilibrium, we actually have an equilibrant vector. And what that is it's taking the combination. So if you have a vector like at this black line, that's our resultant vector. If you go in the opposite direction, so it has the same magnitude, just the opposite direction, that is the equilibrant vector. For example, if you had gravity pulling an object down, the equilibrant would be the opposite direction to that gravity. Okay, so the heading, what that is so essentially when they're saying a vessel being steered, that's basically just any moving object, whether it's a boat or a plane. But your first vector, so here, that's your heading. It's not the resultant. So if this was our initial vector, and then we would have a wind coming down, the bearing, okay, that's your resultant. So the heading vector is not your resultant vector. It's just your first vector that you started for your tail to the head. Okay, so now you have three types of velocities. Your first is your air velocity. So that's just you flying in the air or moving in the air. The next one is the wind velocity. And the final one is the ground velocity. The ground velocity is the resultant. And it's just your velocity relative to the ground, according to the ground. If you look at air velocity, that's the heading vector. So we had just previously, we looked at the heading. So your air velocity would be your heading vector. So in general, when you're doing a lot of these questions, you're going to be asked for the magnitude and the direction. The magnitude is the easy part. You're either using whatever, SOHCAHTOA, sine law, cosine law. It's the direction that's hard. So if we're going to find the magnitude of this, what's wrong with this diagram? So since we're not head to tail here, we have to make it so that it is. So let's move this vector right here, and we're going to shift it to the left. So we have this initial vector, and now we have this vector here, which will also be at 90. So we know this is 2.5, and we know this is 4. And if we're going to do our resultant vector, that's where our resultant vector would be. So to find the resultant, you're just going to do a squared plus b squared equals c squared. So that's the magnitude. Now we still need the direction. Your direction is always going to come from the tail of your resultant, because you're trying to figure out where is that going. So this is our theta here, and we have to try and solve for that. What can we use to do that? That's good. So we'll use tan. So we're going to have tan theta equals opposite, which is 2.5, over adjacent, which is 4. And your theta is approximately, so we don't have to do the true bearing or the quadrant bearing. But with this being said, where would the never eat shredded wheat be for this diagram here? Well, our north would be here. Okay, so this would be our never eat shredded wheat. Now, this vector here is not in the right spot, so if we put it here, and we drew the resultant along there, okay, this angle in here, that's what we just found. That angle was 32, right? So based on the horizontal, we already went 45, then we went 32. What's left until we get to the 90? How would you figure that out? So we take the 90, and we subtract the initial 45 from here. We subtract the 35 that we just found. Or, sorry, 32, thank you. And we end up with 13, which is this small sliver in here. So when we write it, we can say, therefore, at a speed of 4.72 kilometers per hour, we are moving west, and then 13 degrees below the horizontal. Okay, so to start our diagram, we know we're working with a true bearing, so we need our never eat shredded wheat. Okay, and what's the first piece of information we're told? That the bird is flying at 50 degrees at a speed of 200 kilometers per hour. And what is that one? Then we're also told from a bearing of 110. So we're going to be down here around, that's 110. We're also told traveling at 100 kilometers per hour. Now there's something wrong with this. Let's go back to the question, like so, and read this very carefully. It's something you really have to make note of when you're reading these questions. So in this one, we're told that the wind speed is coming from a bearing of 110. If it's coming from a bearing, what that actually means is this is going in this direction. If it's traveling at a bearing of 110, that would be what we just drew. So be very careful with the wording of the question. So if we're going to find something inside the triangle, like maybe this angle, can we figure out what that is? It's 60. Good. Because we went 110, but we can take away that 50 that we already knew. So the inside is 60. So if you have two sides contained by an angle, what can you use? You can use cosine law. So that would be your cosine law. And you should end up with that as your magnitude of the result. We're also asked at what angle. So we still need to find the angle from the tail of the resultant. What can we use for that if we have an opposite side and an angle now? Sine law. We can't use SOHCAHTOA because it's not a right angle triangle. So here we've just shifted so that this triangle at this point is now at the origin. Because we are trying to find out what this angle here is in order to say the quadrant or the true bearing. So it's a little bit easier to say true bearing here because we won't have to do any subtraction. So if you look at this though, right, in our diagram, we've extended this line that way. Can you tell me what this angle here is? So we went 110 this way, and in here, that means to get to 180, what's left over is 70. Now I want you to look at this here. Do you see this X pattern? What do we know about opposite angles inside two lines? Pardon? They're the same. So what does this have to be? 70. We just found out, let me switch colors, that this here, right, based on the pattern that we just did there, in here is 70. So what does this little chunk have to be if we know the whole thing is 90? 20. Yay. So you'd say you're therefore, the speed is 173, and it's at a bearing of 0 to 0 degrees.